Well, welcome to the Cave of Science. We're back here looking at the review from last week's test that you just took. So if you want to retake the test, you may use this as a some review material. One thing I'd like to mention is when you take notes in the Cornell style, what I'm watching is many of you are not taking them on time or copying them to somebody else or watching the notes without listening to the audio, and you're really defeating the purpose of them. If you watch the notes, you listen to them, you write down your material in the Cornell note style, you do your interactive side, you've already looked at the material 4 times. I'll go over the material in class, so that's 5 times. The worksheets reinforce the material, so that's 6 times. And also the activities you do in class reinforces the material again. So really, without even studying, you've gone over the material 7 times. And when you choose not to follow that procedure, you're really defeating the whole purpose. So I hope that you know, kind of get into the routine of doing it that way. Well, on this particular test, we really only had one formula. Wave speed or velocity equals frequency times wavelength. The speed of a wave, pretty much standard metric units, meters per second. Frequency was new to us, which was hertz. And then wavelength, again, length, the standard unit of length, is the meter. The first question asks, what's the definition of a wave? A wave carries or transmits energy. But the key part here, remember, many people forgot this, is that it does not carry the matter that it's going through along with the wave. We talked about Lake Michigan. All the water does not end up on the beach, and air in a classroom does not end up in the back of a classroom. The second question, a piano emits a frequency of 28 hertz. If the speed of sound in air is 340 meters per second, what is its wavelength? Wave speed or velocity equals frequency times wavelength. We have a wave speed, we know the frequency. Very simply, divide each side by 28, and we get a wavelength of approximately 12.1 meters. The next problem asks you what's the difference between a transverse and longitudinal wave? Essentially, you're just given the definition of both. Transverse, the wave travels perpendicular to the motion of the particles. You can see the waves traveling this direction, and the particles are moving perpendicular. In a longitudinal or compressional wave, the wave travels parallel to the motion of the particles. And again, the wave's moving in this direction, and you can see that we have compressions and what's called a rarefaction or an expansion here. So that's a straight definition off the lectures. Problem number 4. A tuning fork produces a sound with a frequency of 256 hertz and a wavelength of 100 or 1.35 meters. Calculate the speed. You did many of these problems in the activities. Wave speed equals frequency times wavelength. Very simply multiply the two together, and speed is 345.6 meters per second. The next question, what must be true about the angle of incidence and the angle of reflection? Again, we have the normal, the incident ray, the reflected ray, and the law is the angle of incidence has to equal the angle of reflection. That was straight off the lecture. You also did that in your worksheet packet that you did in class, and we also discussed that in class. Question number 6, we have a concave mirror, and draw two rays that have a focal point or intersect on the horizontal line. So it bounces off, they intersect. And what's it used for this type of mirror? We talked about the ladies using it, a compact makeup case where it helps to magnify. And this was also right off the lecture, and we did this in class also. Question number 8, for the image above, you can see it's thicker in the middle, so that must be a convex lens. And the use for a convex lens is to magnify. It's also your eye is a convex lens also. Question 9, describe what's happening observer 1 and observer 2. It says the Doppler effect here, and that was strictly right off the lecture, and we also discussed it in class. And so also our observer number 1 is behind the object that is moving in this direction. So you can see the wavelength is longer, so the frequency's got to decrease. As the object is catching up to its own wavelength, it's shortening the wavelength, and it's got a higher frequency. We talked about this in terms of a jet fighter, an F-35. We also talked about it in terms of a NASCAR. The second part of the assessment was the EM spectrum, and really the only difference here, an EM wave can travel through the emptiness of space. The formula was C, which is the speed of light, which I gave you, and the speed of light in a vacuum is 3 times 10 to the 8th meters per second. Frequency is again in hertz, and wavelength is in meters. And this first question is, why can you see the light from the sun, but you can't hear the sun? In other words, what can an EM wave do that a sound wave cannot do? EM waves can travel through the emptiness of space or a vacuum. We talked about this in class. A sound wave needs something to go through. And we mentioned this several times, again in the lecture and then in class. Number 2, determine the wavelength of a microwave that has a frequency of 3 times 10 to the 9th hertz as it travels through space. Well, here's our formula. The speed of light equals frequency times the wavelength. We know the speed of light. We know the frequency. We're going to solve for wavelength. A couple different ways you could do this. You could punch in your calculator, or you could do it the old-fashioned way. 3 times 10 to the 8th divided by 3 times 10 to the 9th. 3 times 3, or 3 divided by 3 is 1. And we know when you divide exponents, you actually subtract them. So times 10 to the 8 minus 9 is 1 times 10 to the minus 1 meters. And again, the standard unit of measurement in the metric system for length is meters. The next question is relate wavelength, frequency, and energy. We did this several times in class, and you were asked to make sure you know as you go from left to right across the EM spectrum, radio waves, micro, IR, vis, and Roy G. Biv, UV, X-ray, and gamma. So as you go from left to right, you start shortening the wavelength, so therefore you get a higher frequency and you get higher energy. So we're just comparing the two. So microwaves versus X-rays. Microwaves have lower energy, lower frequency, longer wavelength. X-rays would have higher energy, higher frequency, and shorter wavelength. Question number 4. Distant star has a blue light wavelength of 4 times 10 to the minus 7 meters. What's the frequency? And again, we know the speed of light. We're looking for the frequency, and we know the wavelength. Very simply, you could have plugged this into your calculator, or you could, again, do it the old-fashioned way. 3 divided by 4.7 is 0.64 times 10 to the 8 minus 7, which would be 10 to the 15th is the frequency. If you wanted to put that in the correct form, it would be 6.4 times 10 to the 14th hertz. If you gave me this answer here, I would have accepted that also. The last problem was Snell's law. And there's one thing we mentioned about Snell's law, you did an activity. As the index of refraction increases, the speed of light will decrease. And so we're going from air, which has the index of refraction of 1, to water, which is 1.33, so the speed of light would decrease. And that's pretty much what was going on in this assessment here. So I hope this helps you, and we will talk to you later.